All right, so this is number 1 on worksheet 5, and we are trying to prove the division algorithm. So the division algorithm says that for all A elements of Z, B elements of N, those are the integers and the natural numbers, there exists integers Q and R such that A equals BQ plus R, where R is greater than or equal to 0 but less than B. So for the proof, we are going to consider the set A minus BK such that K is an element of Z and A minus BK is greater than or equal to 0. So if 0 is an element of S, then B divides A and Q equals A over B and R equals 0. If 0 is not an element of S, then S is still non-empty, because if A is greater than 0, then A minus B times 0 has to be an element of S. If A is less than 0, then A minus B times 2A, which equals A times 1 minus 2B, is an element of S. And if A does not equal 0, and A does not equal 0, since 0 is not an element of S. So that's all cases there. So S is definitely not empty. So now that we've established that, we can use the well ordering principle. So since S is not empty, by the well ordering principle, it has a smallest element R. So we're going to let R equal A minus BQ. Okay, that implies that A equals BQ plus R, with R greater than or equal to 0. Now we are going to assume that R is greater than B. So if that's the case, then A minus B times Q plus 1, which is equal to A minus BQ minus B, equals R minus B, which is greater than or equal to 0 in order to be an element of S. But A minus B times Q plus 1 is less than A minus BQ, which is equal to R. And that contradicts that R is the smallest element. So R has to be less than B. If it can't be greater than or equal to B, then it has to be less than. And then the last thing that we have to do is show uniqueness. So suppose that A equals BQ plus R and A equals BS plus T. For both of those, we have R is between 0 and B, and T is between 0 and B. So basically what we're saying there is that we're supposing that it's not unique, that there exists a Q and an R and an S and a T, different integers for A. So now we're going to suppose that T is greater than or equal to R. Okay, and then BQ plus R equals BS plus T, right? A equals A, and those are both equal to A. So that implies that BQ minus BS equals T minus R. That's just rearranging, which implies that B times Q minus S equals T minus R. But that leads us to, so if B divides T minus R, which it must, right, because we have two products equaling to T minus R, and 0 is less than or equal to T minus R, which is less than or equal to T, which is less than B. But we assumed that T is greater than or equal to R. So T minus R equals 0, which implies that T equals R and S equals Q. And now we have uniqueness.